In this lecture, we're going to introduce logarithmic functions. Logarithmic functions are the inverses of exponential functions. Let's try to find the inverse of f of x equals a to the x. We know that exponential functions are one-to-one. We don't have to check that. We'll replace the function notation with a y equals a to the x. Now we interchange x and y, so we get x equals a to the y. And now what? How do we solve for y? We don't have an algebraic procedure to do this. We know that x equals a to the y is the relation that represents the inverse of this exponential function, but we don't currently have an algebraic way to solve this equation for y, so instead we're just going to make a definition that the inverse function of an exponential function follows this rule. We call that inverse function the logarithmic function with base a. The inverse of the exponential function with base a is called the logarithmic function with base a, and the way that we denote that is with the letters log followed by a subscript. So if f of x is the logarithmic function with base a, we write f of x equals log subscript a, we usually say base a of x. So this is read log base a of x. And actually that's the informal way to read it. That's how I read it. The proper way to read this is to say the logarithm of x with base a, but I kind of read this from left to right and just say log base a of x. That function is the inverse of the exponential function. And that's easy to say, but it's hard to keep in mind because there's nothing about this notation that reminds you of that. So we have this rule, I call this the translator between logarithms and exponential functions. For a positive base not equal to 1, y equals log base a of x if and only if x equals a to the y. There's that equation we ran into when we were trying to find the inverse. So we're kind of describing this logarithmic function in terms of that rule. Two things. First, if and only if can be replaced by a double arrow. So when we write this expression in the future, I'll probably use the double arrow instead of writing if and only if. Secondly, let's break down exactly what this says. We're saying that log base a of x is the y that solves this equation for us. When we go to solve this, we can just say, well, y is equal to log base a of x. Not because of any algebra rule that we had before now, but we're just defining that to be the solution to this equation. This function is the solution to that equation. The way this works is it just follows this translator. The output of log base a of x is the exponent you have to put on a in order to get x. I'm going to say that again. The output of log base a of x is the exponent you have to put on a in order to get x. Let's do that a few times to try to get a handle on this. I've got some examples here. The first one says log base 5 of 25. Let's see what the translator says. It says the output of log base a of x is the exponent you have to put on a in order to get x. Let's rewrite this in that form. We're looking for the exponent you have to put on the base 5 in order to get 25. Well, I'm sure you can just guess at this. We know that 5 squared is 25, and so the output of this is 2. And this is kind of the explanation. We know that 5 squared is 25, so log base 5 of 25 must be 2. Log base 5 of 25 is the exponent we have to put on 5 in order to get 25. Use that same idea to try to find log base 2 of 8. Log base 2 of 8 is asking what exponent do you have to put on 2 in order to get 8. Well, we know that 2 cubed is 8, so log base 2 of 8 must be 3, and the reasoning is that 2 to the third is 8. Log base 7 of 1/7. This is just asking what exponent do you have to put on 7 in order to get 1/7, and we know that -1 is the reciprocating exponent. Since -1 is the exponent we have to put on 7 in order to get 1/7, log base 7 of 1/7 is -1. If you look at this next example too quickly, you might have a knee-jerk reaction. Log base 16 of 4 is not 2. I know 4 squared is 16, but that's not the order here. We ask what exponent do we have to put on the base in order to get the input. Well, the principal square root of 16 is 4, and what exponent represents a principal square root? That's right, 1/2. This is 16 to the 1/2 power. So log base 16 of 4 must be equal to 1/2, since 16 to the 1/2 equals 4. The last example says log base 10 of -100. So here we're trying to answer the question, what exponent do you put on 10 in order to get -100? Well, we've previously covered this. When you put a real number exponent on a positive base, you can't get a negative output. The range of an exponential function is just positive real numbers. Therefore, there's no way that this can happen. 10 to a real number power can never be negative, and so this is not a real number. So summarizing here, the output of a logarithm is the exponent you have to put on the base in order to get the input. Aside from using that translator just to find these values, we can also use it to rewrite equations so that we can solve them. So for example, this says convert 2 to the x equals 5 to logarithmic form. By that we mean write a logarithmic equation that's equivalent to this exponential equation. Let me remind you what the translator says. The translator says that y equals log base a of x if and only if x equals a to the y. We're already in this exponential form and we want to write it in the logarithmic form. Let's just break it down piece by piece. The output of the logarithm is the exponent on the exponential expression. Well, our exponent is x. That goes by itself on one side. The base of the logarithm is the base of the exponential expression. Well, the base of our exponential expression is 2, so the base of the logarithm will also be 2. The output of the exponential expression, the thing on the other side of the equation, becomes the input to the logarithm. The output of the exponential expression was 5, that becomes the input, and we get that x equals log base 2 of 5. Now, in a sense, we haven't really done anything, because the original question was what exponent do you have to put on 2 in order to get 5, and we've got x equals log base 2 of 5, and log base 2 of 5 means the exponent you have to put on 2 in order to get 5. But we'll learn a way to estimate this with the calculator in an upcoming section. And the real point of this is just to practice converting between the two forms. Here's an example going the other direction. Convert log base 2 of x minus 7 equals 6 to exponential form. Here you'll see the power of this rewrite because we'll be able to solve the equation if we were asked to. Let me again remind you of the translator. We say that y equals log base a of x if and only if x equals a to the y. Now we're going from the logarithmic form and writing it in the exponential form. How do we do that conversion? The input to the logarithm goes by itself on one side of the equation. The input to our logarithm is x minus 7, so I'm going to write that by itself on the left side. That's equal to an exponential expression. The base of the exponential expression is the base of the logarithm. The base of our logarithm is 2. So the base of our exponential expression is 2. The exponent on that base is the output of the logarithm. Well, the output of our logarithm is 6, so the exponent becomes 6. And now we have this rewritten in exponential form, which is all we were asked to do. But I hope you could see now we can easily solve this for x. 2 to the 6th power is 64. We add 7 to both sides, and we've solved this equation for x. Again, we weren't asked to do that here, but you can see why we would do this rewrite. We're able to solve this equation for x. Now, there are two logarithmic bases that get used often enough that they get their own special notation. It used to be very common to use log base 10 because powers of 10 are so easy to calculate. Our numerical system is base 10, so powers of 10 are just 1 followed by a bunch of zeros. And so log base 10 got used so often enough that it was just assumed that was the base unless you said otherwise. So log base 10 of x is usually written as just log of x, and we call this the common logarithm. We've learned that base e is very important in exponential expressions, so the inverse function log base e is also going to be very important. We call the exponential function with base e the natural exponential function. And so the logarithmic function in base e is called the natural logarithm, and we denote that by ln x. These two bases get used commonly enough that there's actually buttons on your calculator for both. Down the left side you'll see an log button. That's specifically log base 10, and if you look carefully above that log button, you'll notice that the inverse function 10 to the x is sitting there. So that will be kind of a reminder, almost like a cheat, that the base of the common logarithm is 10. Similarly, you see an ln button. That's for the natural logarithm, and if you look above that, you see the inverse function e to the x. So that's a reminder that the base of the natural logarithm is e. Let's look at some examples that apply these new notations. The first example says the natural log of e to the fourth, and yes, you can put that in the calculator, but the calculator would be offended by that. You don't need a calculator to find the natural log of e to the fourth. Why? Well, we can just use our translator. The answer to this is just an exponent, and in particular, it's the exponent you have to put on the base e in order to get e to the fourth. Well, that's almost insulting. All we have to do is make these match. E to the fourth is equal to e to the fourth, so the natural log of e to the fourth is just 4. The second example says the common logarithm of 1 million. This is 1 million because there are 6 zeros. Well, the base of the common logarithm is 10, so this is asking what exponent do you have to put on 10 in order to get a million. This is easy to do because if the exponent is a positive integer, then that just tells you how many zeros you have when you expand. Since we have 6 zeros, this must be 10 to the 6th, and so the common log of 1 million is 6. Again, you can do that one with the calculator, but we don't need to. See if you can do that last one without a calculator, the natural log of 1 over e squared. If we rewrite this in exponential form, we get e to what power equals 1 over e squared. Well, we know the exponent is going to have to be negative in order to give us a reciprocal, and we're going to need the magnitude to be 2 because we have to square this. So putting those two ideas together, this must be negative 2. Let's try more of these conversions. Let's convert the natural log of x equals 2.6 to exponential form. Our translator says that y equals log base a of x if and only if x equals a to the y. We want to go from the logarithmic form to the exponential form. The input to the logarithm goes by itself on one side. Well, the input to the logarithm is x, so the x goes by itself on one side. The base of the logarithm becomes the base of the exponential expression, and here's where you have to remember, because it's not explicitly written, the base of the natural logarithm is e. The output of the logarithm becomes the exponent, so this is e to the 2.6, and now we've solved this for x. That wasn't what we were asked to do, we were just asked to convert it to exponential form, but as it turns out, rewriting it in exponential form actually solves this equation for x. I want you to try this one. Let's convert e to the 5x minus 3 equals 17 to its logarithmic form. Okay, apply the translator. We know that y equals log base a of x if and only if x equals a to the y power. We're going from the form on the right to the form on the left. The exponent goes by itself on one side. I've written it on the left side here, so 5x minus 3 on the left. The base of the exponential expression is the base of the logarithm. And there's nothing wrong with writing log base e, but we don't typically write that. Instead, we usually write ln for natural log. Both are correct, but ln is the more standard notation here. The output of the exponential expression becomes the input to the logarithm. The output of the exponential expression was 17, so we plug that into the natural log function. This is the natural log of 17. It's not natural log times 17. It's the natural log of 17. Sometimes we emphasize that with parentheses just to make sure. The natural log of 17 is just a number. We could actually approximate it with the calculator. So now we could solve this for x. Add 3, divide by 5. Again, we weren't asked to do that here, but I hope you can see why the conversion is useful. The exponent had the variable in it. The variable is trapped up here. We've now rewritten it in a form where it's easy to solve for x. This is just a linear equation. Let's end with some properties of these logarithms, and we're going to start with 3 rules that I want you to keep in mind. We're going to find log base a of 1, we're going to find log base a of a, and we're going to find log base a of a to the x. The first one says log base a of 1. That's asking a to what power equals 1. Well, we know that any non-zero base to the 0 power is equal to 1. So log base a of 1 is equal to 0. If you think about it in terms of being the inverse of an exponential expression, this makes sense. We know that when you plug 0 into an exponential function, the output is 1. This is the inverse, so that relationship's going to flip-flop. When we plug in 1, the output is 0. The next one says log base a of a. Well, this is asking a to what power equals a. Well, we know that there's an implied 1 exponent on the right side, so this exponent is 1. Log base a of a is equal to 1. and more generally covering both of these rules. You can get this from the translator. This is almost insulting when you write it in terms of the translator. It says a to what power equals a to the x. Well, duh, that's x. But another way to look at this is that we're composing two inverse functions. The exponential function with base a and the logarithm with base a are inverses of one another, and so when you compose them, you get x. That's also true in the other order. We won't see this as often, but if you make log base a of x the exponent on a, those also undo each other, and you just get x. That's composition of inverse functions right there. The last thing I want to do is use the graphs of these functions to talk about some properties. If the base is greater than 1, then log base a of x has this basic shape. It goes through the point 1, 0. We know that from the first property on the previous slide. This has a domain from 0 to infinity, not including 0. That shouldn't be surprising because the range of the exponential function is 0 to infinity. And this is the inverse of that exponential function, so the domains and range flip-flop. Similarly, the range of this is all real numbers. That's the domain of an exponential function. You can see this has an x-intercept of 1, 0. We kind of already talked about that. You'll notice this also has a vertical asymptote. The vertical asymptote is x equals 0. That corresponds to the horizontal asymptote of y equals 0 in the exponential function. This graph is always increasing. It's increasing on its entire domain. It increases on the interval from 0 to infinity. And because it's increasing, that means it's a one-to-one function. Now, we already knew this function was going to be one-to-one because it's the inverse of a one-to-one function. But you can also see it in the graph. Most of those properties are also true when the base is between 0 and 1. The graph is just the vertical reflection of the previous graph. The domain is from 0 to infinity, the range is negative infinity to infinity, the x-intercept is 1, 0. The vertical asymptote is still the line x equals 0. You'll notice this time the behavior is different. As we approach from the right, we go to infinity instead of negative infinity, but the asymptote is still in the same spot. The one glaring difference is that this is a decreasing function, not an increasing function. This decreases over its entire domain. But that still makes it one-to-one because the outputs are progressively getting smaller and smaller. There are no two inputs with the same output. So that's our introduction to logarithms. Again, the main takeaway is that logarithms are the inverses of exponential functions, and basically the output of a logarithm is just the exponent you need on the base in order to get the input. I'd encourage you to play around with these. A lot of people are uncomfortable with logarithms the first time they see them, or even if they've seen them before, you might need to practice them again. So dig up some practice problems where you're just calculating the outputs of some logarithms. Do some conversions between the exponential form and the logarithmic form until you feel comfortable with it. Consider committing these three properties to memory and maybe the fourth one as well. And keep these graphs in mind because we're going to use some of these properties in future lectures. If you have any questions for me, please reach out. You can catch me in an office hour or we can just send emails back and forth.